So our next speaker is Ryssa Moffat, and she's from ETH Zurich, and from the Social Brain Sciences Lab. I think if I got that right.
He forgot to call me a lowly postdoc. So
Next time.
Today, I'd like to tell you about some excessively complicated data that I've collected, and it's a study that doesn't look at children and parents as advertised, but rather intergenerational relationships between seniors and young adults. So bridging populations. So first, I'm going to try and hammer home why naturalistic paradigms need wearable technology, and then talk a little bit about the use cases for these wearable technologies with one and more brains. And then finally, I'll tell you about my own research and an example about combating loneliness using intergenerational art interventions. So wearable optical imaging offers several benefits, and for me, the main ones are that we can have people interact with real environments, physical environments, as well as virtual environments using VR, but also with other people. And so, as I've just suggested, one of the strengths of this type of imaging is that you can combine modalities quite easily. So you could combine fNIRS or maybe one day DOT with fMRI, EEG, and VR, which allows us to capitalize on the strengths of each of these modalities. The naturalistic paradigms that we can use can help us understand how people navigate spaces with different characteristics and in different circumstances, how they interact with each other, how interactions unfold dynamically, and we don't have to limit their gestures, their body movements, or their head movements for that matter. It's quite exciting that we could actually have ecologically valid neuropsychological assessments measured in real time, and that we can track the progression and rehabilitation of motor disorders, auditory disorders, and cognitive disorders, as well as affective disorders. All of these disorders could possibly be targeted using wearable technologies and providing neurofeedback. So there's lots of exciting avenues here. And a couple more kind of specific examples. So lots of people are interested in measuring one brain at a time to understand cognition more deeply. There's a lot of push right now to understand how people find their way through spaces and navigate. And there's also some really exciting research going on to understand how people's cognition changes when they're stuck in extreme environments. So for example, if you were in a space shuttle for several days, isolated, or if you were doing research at the Antarctic research centers, how would your cognition be changing over that time? And then in clinical settings, wearable technologies that measure brain activity using light can be really useful for understanding the development and rehabilitation of disorders of the consciousness or motor disorders, and also for helping premature babies and other babies born on time. It's also possible to use this technology to measure more than one brain at once. And for me, it's particularly relevant because we can look more into social interaction. And this social interaction doesn't have to be limited to two university students sitting at a table playing games, but rather it can be in people's homes in very natural settings for them, and even involve more than two people. So here we have an example of a multi-generational family interaction, or where people take different roles, for example in a clinic with a client and a therapist, or in school classrooms with teachers and students. And it's also possible to look more deeply into how complex tasks are accomplished, whether it's audio, visual, and motor integration, or complex motor coordination, so for example, playing in an orchestra or conducting a difficult surgery. All of these are possible. And now, you might be wondering how my example links up with this. My example specifically has to do with intergenerational collaborative art making, so social interaction, and the purpose is to see how we can combat loneliness and understand what's going on in the brain and the body. Loneliness is a very important problem to consider. Loneliness puts us all at risk for poor health and death, and it's most prevalent in young adults and seniors. The World Health Organization estimates that 1 in 4 seniors globally is currently socially isolated and lonely, and the World Health Organization has conducted a scoping review of over 3,000 studies demonstrating that art interventions are likely to reduce loneliness and promote health. In their scoping review, they also encourage in-person interventions over digital interventions. And this is timely because we're currently also seeing a push for social prescribing, where doctors are actually prescribing their patients more social interaction through interventions that may or may not involve art. The benefits art interventions specifically have to do with increased physical and social health, and this is achieved by helping people bridge social gaps in their lives, whether those are generational or simply social, and it helps people, old and young, reduce the stereotypes they have against other generations. And so we designed an art intervention that will help us map the role of brains and bodies in new and budding intergenerational relationships. And it's my hope that we can use the information from my extremely large study to inform policy and encourage funders to put money towards programs that can help us reduce loneliness for people of all ages. This study involves 4 parts. We're tracking intergenerational collaboration. We're gathering longitudinal insights over 6 weeks, and we're tracking people's social well-being, as well as how they align with each other in their body movements, their brain activity, and in their heart rate. And so some of the theoretical bases that you might be wondering about start with, why do people align? It's suggested that this is how we form relationships and maintain relationships, and it could start with, in the form of processing, it starts with making sure that we're actually aligned with others. And we do this by processing sensory inputs of our own selves and of others, and this happens in the dorsal anterior cingulate cortex, the dorsal medial prefrontal cortex, the anterior insula, as well as the temporal parietal junction. If there's a mismatch, then we see that the networks involved in action, observation, and execution are recruited, and this involves the inferior frontal gyrus, the inferior parietal lobule, and the premotor areas. And these areas serve to update the prediction so that alignment can be maintained. If there's no mismatch, then reward areas are involved. The orbital frontal cortex, the ventral medial prefrontal cortex, and the ventral striatum keep the prediction, all with the aim of maintaining alignment. And so the other side of the theory that I'd like to bring up is that it's important to understand why we might measure 2 brains at once and what we're trying to get at. When 2 people watch a movie, we would assume that the stimulus is similar for both of them and might evoke similar patterns of brain activity. And if they do this sitting beside each other, we might think about the processing between the 2 of them being common between the 2 people. And then on the other hand, if 2 people are interacting with each other, the stimulus is then the other person, the interactant. And here, we expect mutual prediction. Each person's prediction of the other person's behavior is actually the stimulus that would cause the brains to become aligned and have some form of entrainment. So in the study that I have run, at this point we've collected the data and we're in the early stages of the analysis. We invited 122 strangers into the lab, and we paired them up into 61 dyads. The dyads stayed the same, and every dyad came in 6 times, about once a week. Half of the dyads were same generation dyads, so 1 person aged 18 to 30, or 2 people aged 18 to 35, and the other half were intergenerational, 1 person aged 18 to 35, and 1 person 70 plus. At each session, all our participants completed questionnaires. At the first, they completed an empathy questionnaire, and then at every subsequent session, they completed questionnaires on loneliness and how close they felt to their partner, and how they perceived their own generation and other generations. And we recorded their brain activity at all 6 sessions, as well as motion capture of their body movements, and how they felt about the interaction in qualitative feedback at the end. And after the final 6th session, we interviewed them all for about 20 minutes, so we have a lot of rich qualitative data to work with eventually. Just to give you an idea of the scope of the data collection, we have 732 fNIRS recordings, each of about 25 minutes, which comes out to something like 300 hours of recording. And this was possible because the setup and the cost didn't hinder our progress. So specifically to the fNIRS recordings, we recorded over areas that are relevant for social processing, the inferior frontal gyrus and the temporal parietal junction on both hemispheres. And our setup had, each cap had 10 LED sources and 10 detectors, and our sampling rate was about 5 hertz. Because our participants came in 6 times, and it's important to know that we were measuring from the same brain areas every time, we digitized the caps without the sensors so that we could understand in coordinates where we were measuring from, and with those coordinates we could choose to exclude any channels that had move too far away from the center of our ROIs. At every session, again, the participants completed questionnaires, and then we scanned their head to make the 3D model. We finished the fNIRS setup by putting all the sensors into the cap, and then they first drew alone once, and then together twice, and then they did collaborative activities, after which they answered a questionnaire about how close they felt to one another and provided their personal feedback about how they liked the session and what they experienced. When they were drawing alone, it looks like this. There's a felt divider between them so that they can't see what the other person's drawing. It's possible they can hear the oil pastels moving on the paper, but they have no visual input about the other person. And so this is a type of co-presence that might evoke common processing because they're doing the same task. When they're drawing together, they can see each other. They're drawing on one piece of paper with no instructions in either case, alone or together, what to draw, how to draw, but they are instructed in both cases not to talk. And this makes our alone condition very comparable to the together condition. We analyzed the brain signals to look for similarities using wavelet transform coherence, which gives us a measure of the correlation of the two signals in the temporal and frequency domains. We achieved this using a very cool package created by Guillaume Dumas in his lab, which is called HiPipe. And the visual identity of this package should be a snake emoji, a wave emoji, and another snake emoji to visualize the hyperscanning between snakes, which mean Python. And I apologize for the new version. And then I guess it's important to think about how we can actually tell that the synchrony between brains means something. So when we do hyperscanning analyses, we first compare the level of synchrony that we see between people who really interacted versus the level of synchrony we see in people who never met. They completed the experiment, but never together in the same room. And so here we have the solid lines visualize real pairs, and the dashed lines visualize pairs of people who never met. And then when we compare these levels in the different pairs of brain areas, here again we have solid lines visualizing areas that had higher coherence for real pairs than pseudo pairs. And where you see dashed lines, that's where the difference between pseudo pairs or fake pairs and real pairs was not meaningful. In 4 of these areas, we see differences between drawing alone and together. So in the left temporal parietal junction of both participants, in the right IFG and left IFG, the right IFG and right TPJ, as well as the right IFG and left TPJ, we see that coherence, while people collaborate on drawing together, is higher than when they draw alone. Only for drawing together in the left temporal parietal junction, and only for drawing together in the left temporal parietal junction do we see a difference between groups where the intergenerational pairs show higher coherence than the same generation pairs. Because this was a longitudinal study and we're starting to dig into the analysis of how coherence between two people's brains changes over time as they get to know each other, I'll give you a sneak peek. And in this same pair of brain areas, the left temporal parietal junction, we see that specifically for drawing together, the intergenerational pairs' levels of brain coherence are increasing the more they get to know each other. To make sense of this, I'll just jump back to the theory a little bit. I mentioned the idea of common processing, so seeing the same stimulus and having similar patterns of brain activity, and having actual mutual prediction, which is based on the other person's behavior. And then the idea that the brain is constantly, if we're trying to align with someone, the brain is constantly tracking mismatched and matched expectations. And so if we think about the fact that we saw greater coherence while pairs were drawing together than alone, it would suggest that this collaboration is evoking mutual prediction, and that the specific relationships that we saw in the left temporal parietal junction, where there was greater coherence for intergenerational dyads while they were drawing together than same generational dyads, and that this coherence showed an increase from the first session to the 6th session where they knew each other better, suggests that the mutual predictions that they're making may be matched more often, and that this might be actually increasing as they get to know each other and become more familiar with each other through our art intervention. And so the takeaway for now is that intergenerational collaboration seems to develop differently than same generational collaboration. And because this is a naturalistic paradigm, we actually have a lot of data that we really should be exploiting to make sense of it. So we have to go through the behavior and link it up with the findings that I've just shown you to really understand how this collaboration is developing. And just a little recap about the very exciting ways that we can use wearable optical imaging to advance the field. We have lots of opportunities for naturalistic paradigms, for multimodal measurements, for ecologically valid assessments, and for continuous observation in clinics, as well as neurofeedback. There's lots to be excited about, and I would like to thank the people who've helped me with this project so far, including Karan Dash, who gave us art materials, and Cortivision, who loaned us the devices we used. And then if you haven't seen my poster yet, it'll be up tomorrow, and I'll be standing to discuss some other findings from the project. Thank you.